L'Hopital's rule gives us a way to evaluate certain limits. Those limits are of a very special form. So let's talk about that. It looks like L'Hopital's rule, and different, to make it even more confusing, different books spell it differently. So suppose, here's the idea. Suppose that f and g are differentiable functions near x equals a, except possibly at x equals a. That's not so important. And g prime of x doesn't equal 0. Also assume that the limit as x approaches a of f of x equals 0 and the limit as x approaches a of g of x equals 0. Okay? Or an alternative is they could both approach plus or minus infinity. Now, they don't have to both approach plus infinity or both approach minus infinity. It could be either or. Then, it turns out, believe it or not, this looks like magic, but it turns out that the limit of f of x divided by g of x as x approaches a is exactly the same as the limit as x approaches a of f prime of x divided by g prime of x. Isn't that neat? Right? Now you might be asking, why the heck is that true? But sometimes when you take derivatives, functions get simpler. And the idea is maybe you don't know what the function, what the limit of f of x over g of x is, but maybe it will become clear what the limit of f prime over g prime is, as you'll see. And now this is assuming, you know, the limit on the right-hand side exists or is plus or minus infinity. Okay. So why might this be true? At this level, I don't have a good proof for you, but you guys do know from Calculus 1 that the kinds of functions we look at in calculus, if you zoom in on them, they look like lines, right? They look linear. Those are the kinds of functions we concern ourselves with. So let's suppose that we have a function f like that, and let's suppose it goes through, so it's some curve, and it goes through a0. So certainly the limit of f of x as x approaches a is equal to that a equals 0, right? Or that second coordinate of 0, I should say. And let's suppose that in other words, the x-intercept of f is at a0. And let's suppose the x-intercept of a function g is also at that value. Let's say it looks like that, and let's say that function is g. And so certainly the limit as x approaches a of g of x is also 0. So it satisfies the first criteria that we mentioned in L'Hopital's rule. But now zoom in. So imagine creating a box here, and you zoom in on that box. And so zoom. And so that box gets bigger. And so maybe all you see is the x-axis and that intercept at a0. And then maybe the graph of g looks kind of linear now, right? And maybe the graph of f, since you've zoomed in, looks kind of linear now. And the more you do that, the more it will look linear. That was a huge idea from Calculus 1, right? So we could approximate the equation of f using a line. And in fact, you can show pretty easily using pretty basic algebra that f would approximately be equal to whatever the slope of that line is, we'll call it m1, times x minus a, that x-intercept. So you can prove that using the formula y minus y1 equals m times the quantity x minus x1, which is called the point slope form from algebra. And maybe g, is going to be approximately equal to some slope m2 times x minus a. Okay? So then what would f of x Well, let me put it over here. What would f of x divided by g of x look like? Well, approximately, and as you zoom in, it gets better and better, m1 times x minus a divided by m2 times x minus a. But on that right-hand side, what's going to cancel out? The x minus a, and you get m1 over m2, which is f prime everywhere, but you could say at a, divided by g prime. Let me be more general here, since we're going to be talking about limits. Let me use x. So that is f prime of x divided by g prime of x, because for lines the derivative is constant, right? So it's an indication on why it might be true. It's nowhere near a proof. So what we're saying is then it doesn't matter. As x approaches a, then this will be true, okay? And so it's an indication. It's nowhere near a proof. In a more advanced class, you would do a rigorous proof of L'Hopital's rule. So let's show you some examples of using L'Hopital's rule to evaluate limits. We're going to evaluate the limit as x goes to 0 of e to the 2x minus 1 divided by x. So one of the critical things you do here is determining whether or not you can apply L'Hopital's rule in the first place, because it's only a select number of kinds of limits you can do that with. So let me show you how we think of the criteria I mentioned above. So remember what we're looking at. We're looking at a limit of some kind of ratio that looks like this, right? And it turns out that the limit of f as x approaches a has to equal 0 or infinity, plus or minus infinity. And the limit of g has to equal 0 or plus or minus infinity. So if upon direct substitution of the value that x is approaching, you get something of the form 0 over 0 or plus or minus infinity over plus or minus infinity, then you have the right, what we call indeterminate form, to apply L'Hopital's rule. So what all this is saying in more simple language is upon direct substitution, and I'll talk more about what that means in a second, upon direct substitution of a, the value that x is approaching, you get either something of the form 0 over 0, which is not necessarily undefined. This might be the first time you've heard that. It's indeterminate. Or plus or minus infinity, one or the other, over plus or minus infinity. These are called indeterminate forms, and they're the right indeterminate forms to apply L'Hopital's rule. So what I'm going to do is I'm going to use an arcing arrow. I don't want to use a straight arrow because that's notation that's a different notation for limits. So what I'm going to refer to after that arcing arrow is what we get upon direct substitution. So what happens when you substitute 0 in for x right there? You get e to the 0, right? Which is what? Minus 1. So on top you get 0. On bottom you get the indeterminate form 0 over 0. Right? It's the correct indeterminate. There's other indeterminate forms, by the way. It's the correct indeterminate form to apply L'Hopital's rule. So I just want to see some squiggles about that. Okay? Okay, there are more than squiggles, but you get what I mean. So now let's apply L'Hopital's rule. So according to L'Hopital's rule, this limit then, a fairly complicated looking thing on top, becomes the limit as x approaches 0 of the derivative of the numerator over the derivative of the denominator. What's the derivative of e to the 2x? 2e to the 2x, right? Minus the derivative of 1 is 0 over derivative of x is 1. That's a simpler looking function, isn't it? By the way, let's indicate when we apply L'Hopital's rule with a little h. Now, it is as x approaches 0. So does 0 cause any problem with, upon direct substitution, does 0 cause any problem here when you plug 0 in for x? No, so you can just directly substitute that in, right? And then you just get 2 times e to the 2 times 0, but that's e to the 0, which is 1, and you get 2. So we would actually say that this limit converges to 2. So we would say the limit converges, if I could spell, we would say the limit converges to 2. We say it converges when it approaches a single number. Second example. Let's take the limit as x goes to infinity of natural log of x divided by x. Okay, you guys tell me, what do we have to verify first? Is it indeterminate form upon direct substitution? What do we get? Now, it's an abusive notation, you guys, to say we can actually plug in infinity, right? Infinity is not a number. So this is the only time you're ever allowed to do this, okay? To actually plug in infinity into a function when you're determining if it's an indeterminate form upon doing so. So, well, okay, let's think about the natural log function. Before I draw a conclusion here, let me draw a graph. Do you guys remember what the graph of the natural log function looks like? Kind of like that, right? The y-axis is an asymptote. But really, we're saying x is increasing without bound here. So what's happening to this graph, the height of this graph as x goes to the right without bound? The height goes up. So what does the natural log of x do as x goes to infinity? It goes to infinity. So upon direct substitution, you get infinity, right? And then what does x do? As x gets bigger and bigger without bound, what does x approach? Infinity. So is this one of the correct indeterminate forms? You bet. So that's what you have to check, okay? L'Hopital's rule applies. Okay, so what then does this limit equal? This limit equals it's the same as the limit according to L'Hopital's rule, so we're applying L'Hopital's rule right here. Put a little h above the equal sign. The limit, okay, take the derivative of the numerator, the derivative of the denominator. What do you get? On top you get 1 over x. On bottom you get, what's the derivative of x? With respect to x, 1, right? Now is this something you know how to take, if we clean it up, I guess. Yeah. Is that a limit you know how to take from Calc 1? Yes. Okay, numerator stays the same, 1 over x. The numerator stays the same. Denominator increases without bound. What's its value? 0. And that did not turn out to be the right thing. There we go. That looks better. L'Hopital's rule makes weird-looking limits, limits of weird-looking functions, I should say, makes those look easy, right? I feel like I'm selling you L'Hopital's rule. Okay, the other indeterminate forms include 0 times infinity, 1 to the infinity power, infinity to the 0 power, 0 to the 0 power, and infinity minus infinity. Now, what's happening is an epic battle when you get these indeterminate forms. 0 times infinity, normally 0 times a number is 0, right? And you would think that normally if you could multiply, infinity times most numbers would be, positive numbers would be infinity, right? Negative numbers would be negative infinity, right? But then as an epic battle, it's like the Justice League versus the Avengers, right? And if you don't know what that means, you're not nerdy enough. We don't know who's going to win. So it's an indeterminate form. Same with 1 to infinity. Normally 1 to some power is 1, right? But it turns out to be an indeterminate form in the right situation. So these are more indeterminate forms, but L'Hopital's rule doesn't apply. So hopefully we can write, if we have something in the form 0 times infinity. Hopefully we can write it in a form where we can use L'Hopital's rule. Okay, example, evaluate the limits. Part A, the limit as x goes to infinity of e to the negative x times the square root of x. Let's talk about the indeterminate form, you guys. Now, here's where I need to draw you a graph and remind you what the exponential function looks like. The exponential function e to the negative x actually looks like this. When the exponent is negative. So it's like you're graphing y equals e to the negative x here. X is going to infinity, so what does the graph appear to do as, what does the graph of e, the function e to the negative x do as x goes to infinity? It approaches a height of 0. The x-axis is an asymptote, in other words. So it looks like this function, e to the negative x, approaches 0 as x approaches infinity. And what does the square root of x do as x gets bigger without bound? What's the square root of infinity? Yeah, okay. I mean, it doesn't mean anything to say the square root of infinity, but at least in our minds, it allows us to reason, oh, that should be infinity. So we get an indeterminate form, 0 times infinity. L'Hopital's rule does not apply to this form, but maybe we can use algebra to rearrange the guy we're taking the limit of so that it is the correct indeterminate form. So is there a way to rewrite the given function so that we get like 0 over 0 or plus or minus infinity over plus or minus infinity? What do you guys think? I think a natural thing to do would be to rewrite e to the negative x in the numerator as e to the x in the denominator. Now, the graph of e to the x, if you graph e to the x, it turns around and looks like this, right? It's the reflection of the graph in red across the y-axis. And what does this guy do? What does the graph in blue do as x gets bigger and bigger without bound? It goes to infinity. So the denominator rather becomes infinity upon direct substitution. The numerator, it's still square root of x, so it's still infinity. Now, what about infinity over infinity? Is that one of our forms? You bet. So L'Hopital's rule applies. So here we go. We're going to take the derivative. We're going to keep the limit notation in front, you guys. Don't lose your limit notation. Take derivative of the numerator and denominator. That's what L'Hopital's rule says. The given limit's going to equal or the limit I wrote down in the second step is going to equal the limit I'm about to write down. So what's the derivative of the square root of x? Well, it's x to the 1/2 power, so 1/2 x to the negative 1/2, right? Over, what's the derivative of e to the x? E to the x. Okay. How can I rewrite that? Could I bring the x to the negative 1/2? Could I bring it down and write x to the 1/2 in the denominator as a factor? In fact, that would leave me with just 1 in the numerator, wouldn't it? Yeah. Over 2 times, okay, square root of x, x to the 1/2, right? And then times e to the x. Does that seem reasonable to you guys? Okay, what's happening to the denominator then as x gets bigger? Square root of x goes to infinity, e to the x goes to infinity, the denominator is going to infinity. What's the numerator doing? Staying the same. So what happens when the denominator blows up and the numerator stays the same? It goes to 0, so that's it. That's it. And this is a neat little example. What if we had the limit, let's say the limit as x goes to infinity. That's a horrible infinity symbol. There's a little better one. Okay, 1 plus 1 over x to the x power. What's the form here? What's the indeterminate form? Okay, so inside the parentheses, what happens to the 1 over x as x goes to infinity? What's happening to this term? Goes to 0, right? And what's happening to this term? 0 to infinity then is our, 1, I meant to say 1 to infinity is our indeterminate form. So it's an epic battle, right? Who's going to win? Is this going to be 1? Is it going to be infinity, this limit? Is it going to be something in between? It's an epic battle. By the way, the indeterminate form 1 to the infinity, is that one of the forms that we can use L'Hopital's rule on? No, can't do it. So we need an idea here. What could we maybe do to get that exponent to fall down? Yeah, okay, first let's set it equal. Let's set y equal to that limit. And then the idea is, let's take the natural log of both sides and then take advantage of the power rule for logarithms, right? So if we take the natural log of both sides, we get this. On the left side, natural log of y. On the right side, the natural log of the limit as x goes to infinity of 1 plus 1 over x to the x. So I had a couple people ask me after class, I kind of mentioned quickly why we can actually bring the limit to the outside or ln to the inside, however you think about it. So let me spend a little bit more time on that right now, since it provided some confusion. Let's put it this way. Let's suppose you have a function f of g of x. It's a composite function, right? And you're taking the limit as x approaches a of f of g of x. Then the question becomes, when can we bring the limit inside? When can we rewrite this as f of the limit as x approaches a of g of x? When is that legal to say that that's true? It's legal to say that that's true when f is continuous. So that's something, and believe it or not, it is something you learn about, or you should learn about in Calculus 1. We're not going to try and prove it here. Now, if g is continuous, all the better, because if g is continuous, then you can use direct substitution and just plug a in for x and evaluate the limit that way. But to move the limit in, we don't require that g be continuous. In fact, it may be an indeterminate form. So is the natural log function continuous on the domain we're interested in? Yeah, it is. So that's what allows us to bring the limit to the outside or the ln to the inside, however you want to think about it. So I'm going to rewrite this then as the natural log of y equals the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x. And that's important to be able to bring the ln to the inside, right? Because now we can apply the power rule for logarithms. And what are we going to get if we do that? After the limit symbol, we're going to bring this dude down in front like that and have x times the natural log of 1 plus 1 over x. But is that the right indeterminate form as written? So after the limit symbol, do we have the right indeterminate form to use L'Hopital's rule? What do we actually have upon substitution? Infinity times, well, okay, guys, if this guy is going, where is this guy going? 0. And then what's the natural log of 1? 0. So this guy, natural log of this 1 plus 1 over x is going to 0. So we're getting the indeterminate form infinity times 0, which is not something that's okay to use L'Hopital's rule on. Is there a way to rewrite this? So we have x times natural log of 1 plus 1 over x. Is there a way to rewrite it so that it is okay to use L'Hopital's rule? Well, what do you mean by that? Okay. So you're thinking about the trick from the other day, right? Multiplying by x, or x over 1 if you like, is the same as dividing by 1 over x, isn't it? So let's see if that helps us. Sometimes you just want to try it, see if it's going to work. So if I rewrite it as the natural log of 1 plus 1 over x divided by 1 over x, that's the same thing as multiplying by x over 1. And now is it the right form? What do we still have what? From the natural log of 1 plus 1 over x, the limit of that as x goes to infinity is 0. So we have 0 on top. And what about 1 over x as x goes to infinity? 0 on the bottom. When you're checking for the indeterminate form, that's the only time it's okay to plug in infinity, okay? Otherwise, you're going to write out the limit notation. Because you can't actually plug infinity into any functions, right? It's just a convenience is why we're doing it, to check the form. Okay, so that's the right indeterminate form to use L'Hopital's rule. Okay, so what does L'Hopital's rule say? It says that this limit will be the same as the limit of what? As x goes to infinity. The derivative, respectively, of the numerator and denominator of that fraction we just created. Okay, well, what's the derivative of the numerator? Natural log of 1 plus 1 over x? How about 1 over 1 plus 1 over x times the derivative of what's inside by the chain rule. So okay, this is the inner function. I'm still working on the derivative of the numerator. What's the derivative of 1 plus 1 over x? No, I think you're thinking of an integral. So it's negative 1 over x squared. Is that what you're telling me? Yeah. The derivative of 1 over x, think of it as x to the negative 1 power. Use the power rule for derivatives, and you'll get negative 1 over x squared. In fact, I'll put it in parentheses here. So that's by chain rule. So that's the derivative of the numerator. Does everybody agree with that? I'm not going to simplify it yet because I don't need to yet. What's the derivative of the denominator, which is 1 over x? The derivative of 1 over x is? Negative 1 over x squared. So now you see why I didn't simplify, because this entire negative 1 over x squared will cancel with this one. Everybody see that? Let's clean it up. We get the limit as x goes to infinity of just this guy, 1 over 1 plus 1 over x, which is actually something we can evaluate. By the way, it was L'Hopital. If you want to indicate L'Hopital's rule, it was in this step right here. So put the little h right there. This is something we can just evaluate, right? What happens to 1 over x as x goes to infinity? 0, and then what's left? 1 over 1, or just 1. So, trick question, are we done? It's not really a trick question, it's just an important question. We're not done, right? Because, go back, and what was the left-hand side of the equal sign? ln y. So ln y is equal to 1. So how do you get y is the limit we're interested in. How do you get y out of that? Yeah, there's a couple different ways to think about it. You could think of putting both sides as the exponent of e, because if exponents are equal, on the same base, it'll still be a true equation. And E and natural log are inverse functions, so the guy that falls down from this guy over here is just y. So a lot of people like to do it that way. So y equals E, that mysterious number 2.718 blah, 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 that turns up in so many different applications in math. Everything from compound interest applications to population growth to AC circuits. E is everywhere in math. Not everywhere, but it's in a lot of places. So that's kind of interesting that we just developed another definition for E. Oh, by the way, it's also the base of the exponential function, right? Which is an interesting function all by itself. Why is that an interesting function in calculus? Well, it's its own derivative, right? So we just came up with another definition for E. It's the limit as x goes to infinity of 1 plus 1 over x to the x power. Okay, so it is finite. So I guess in that epic battle between 1 and infinity, I guess it's not equal to 1, but it's in between 1 and infinity. It's a lot closer to 1, so you're always a lot closer to 1 for any finite number than you are to infinity. So I would say 1 won that epic battle.